E.W.O encourages us to do lateral thinking, and his books contain delightful examples. Well, here's a beauty you might like to add to the collection. Gyroscopes do not exhibit a new force. They show a lack of a force where there should have been one. That's why it was so hard to see. A lack of centrifugal. "I see nobody on the road," said Alice. "I only wish I had such eyes," said the king in a fretful tone. "To be able to see nobody, and at that distance too." Lewis Carroll must be laughing at us all. If there is a lack of a force, the rest is just pure engineering. We have not yet covered all the situations, especially the radiation one. But above all, never forget, beware the Jabberwock, my son. The jaws that bite, the claws that snatch. There are many heads and many claws, but what an adventure. The Jabberwock was a monster with many heads. It was as if it was, for me, a representative of the way we divide our science into physics, chemistry, biology, and then we take one of those, like physics, and we divide it into heat, light, sound, electricity, and magnetism, then we subdivide that, and so on. Now, some of these heads of the Jabberwock are really laws of physics, I suppose, for me, and some of them look into mirrors and see their own reflections, and they then think there are more of their kind than there really are. One of the things that you may not have been made sufficiently aware of is that there is apparently no simple connection between gravitational mass and inertial mass. When you compare two masses, you can do it either by weighing each on the same spring balance, or by subjecting each to a known force and measuring its acceleration. And the two methods always agree in the answers absolutely. And so, although there's no simple connection, these two heads of the monster must in some way be a curious kind of reflection, the one from the other. A coil of wire in 1830 was said to have a property all its own, which was called resistance. This was a property of this coil. You could measure it by measuring the ratio of the voltage across it to the current flowing in it. So I will pass some DC into the coil. Sorry, I beg your pardon. Yes, we will. Pass AC into this coil. We've got about 5 amps of it, have we? No, less than that. We want some more. That's it. About 5 amps of that, yeah. And then we can use a second coil merely connected to a voltmeter. When I put this second coil on the top, it gets some induced voltage by a mechanism which I do not understand, and I suspect that neither does anyone else. But if I turn this second coil at right angles, it's always been our experience, you can find a place where the voltage is zero, as long as the coils remain at right angles. It's as if they lived in separate worlds and didn't want to know about each other. Now, in that respect, I was reminded by a drawing by M.C. Escher, who's done many marvelous drawings, that it was like the drawing of the men on the staircase. And of them, the artist himself said, here we have 3 forces of gravity working perpendicular to one another. Here is an artist being more of a scientist than we are ourselves. 3 earth planes, he said, cut across each other at right angles, and human beings are living on each of them. It is impossible for the inhabitants of different worlds to walk or sit or stand on the same floor, because they have different conceptions of what is horizontal and what is vertical. Yet they may well share the use of the same staircase. On the top staircase, illustrated here, 2 people are moving side by side and in the same direction, and yet one of them is obviously going downstairs and the other upstairs. Contact between them is out of the question, because they live in 2 different worlds and therefore can have no knowledge of each other's existence. They remind me sometimes of a chemist and an engineer. Although the artist has only used a trick of perspective to influence the mind of the observer, it is a lively, healthy influence indeed for me. Gyroscopes are essentially circular things, A scientific gyro is usually mounted in gimbal rings, so that there is the wheel, here is the inner ring, here is the outer ring. All three sets of pivots, the axes pass through the center of mass of the gyro. Now I will tell you what precession is. A torque, by the way, is a twisting force. Instead of push, which is a force, you push a thing which is pivoted and it twists. So torque is a twisting force. The result of the twisting force is a movement, a rotation, but not in the axis in which you applied the torque. And we call that precession. So I put a torque on the outer ring, it is the inner that precesses. I put a torque on the inner ring, it is the outer that precesses. It will work in either direction. Oh, you're cheating, I can hear my critics saying. You're pulling it round as well as doing that. All right, we will satisfy the critics. We will hang a weight from the inner ring so that gravity and not I shall put on the torque. And there you see a precession. Not the sort of movement you really expected, because you are accustomed in higher mathematics to a torque producing an acceleration. Here, a torque produces purely a rotation. And if I put 3 times the mass on, I get 3 times the angular velocity. A different sort of device from our common experience. Now, what I want you to notice this time is, I'll spin it up again because it's getting a little slow. I want you to notice how it accelerates when I put the weight on and how it decelerates, especially how it decelerates. Having been convinced that a torque produces a velocity and not an acceleration, it must have an acceleration or it couldn't increase its velocity at all. And it must have a deceleration when it stops. So let us see if you can determine the rate of deceleration from that sort of angular velocity. When it comes round, I'm going to catch the weight and watch it stop. Hop. Ready again? Hop. There is an acceleration, but it is of a simply enormous value. Toy gyros are usually supplied with a little Eiffel Tower model, and one of the standard tricks you're supposed to do is to spin the gyro, put it sideways on the tower, thus allowing the force of gravity down on that to be reacted by a normal force from the top of the tower. So you're putting a torque on about a horizontal axis, and that will make the gyro precess about a vertical axis, and everyone is amused. And no one takes it seriously because it is, after all, a toy, isn't it? Fine. Most interesting demonstration. Let us just weigh these two things. First of all, we will weigh the gyroscope. Where's the old there? That's it. We will weigh the gyro, and we find it to be 310 grams. There are 312 grams. We will weigh the tower and find it to be less than a gram. So over 300 times the weight of the tower. Now, haven't we missed something? Thank you, Bill. What did we miss? We missed the fact that if you ever try to rotate something which is eccentric, not symmetrical, you tend to... Yeah, somebody knows, they've tried. You tend to shake your bones to pieces. Now, what is happening when I do that? Apart from me getting in terrible shaking, the whole of this is trying to retain its center of mass fixed. Let us look at the gyro again with that sort of thought in mind. Surely 300 grams compared to 1 gram, you would expect the 300 grams to want to stay in the same place and you'd expect it to move the tower around itself. But of course it is our common experience that although that happens, the gyro on the tower does not make the tower go round the gyro. 300 times the mass. Whoops. Sorry about that. Can you screw back in his bearing? Friction on the table. I can hear my critics now. He has friction. We thought we would remove as much of the friction as we could by spinning it on ice. This, of course, is an adjustable gyro. This belongs to an earlier age. Nowadays, they make the flywheels out of aluminium, and what better metal than something that's one of the lightest we know for making a flywheel. So, there it is. This is the modern high standard of living. This is an old-fashioned gyro, about 30, 40, 50 years ago. We have some gyros here today that are 100 years old. So here's a thought. This thing has been with us for 100 years. And we haven't noticed those things which we might have noticed. A tower on ice. Are you convinced? I was. We go to this machine, which has little buckets around the outside so that I can blow air on them and get it spinning to a quite high speed. Something like 5,000 revs a minute. Don't be alarmed by the noise. When we get this 8-pound wheel up to speed, I shall take a pin out there to allow it to flop like this, and then we shall do experiment number 1, which is to search for centrifugal force. If I bring out the gyro to that position, it is free to topple over. I shall need, in fact, a little weight to hold it down. Of course, in any other position, it's all right. It's only when the offset mass comes out there that it weighs over like that. Now, we'll spin this up, and then I'll take the weight off and ask Mr. Coates to catch the gyro as it falls. Now, if you'll come round there and ready to catch it when I lift the weight, next time round it's coming off. He cheated again, says the man in the gallery. Did he really? Yes, he pushed the aluminium back a bit. All right, he'll pull it forward a bit. More than a bit. Pull it forward a lot. The whole of the tower is now well outside the end of the bench. And if you want me to prove it, I'll show you what happens when the wheel is stationary. Again, it doesn't require much catching, you see. It's gentle as a lamb. Now we'll put the pin back in, and we'll see by how much it overbalances. Well, a lot, obviously. How much? That much? Oh, a lot more than that. That much? More than that. That's it. That much. Over 2 kilograms. Out of balance. And if that looks a ridiculous thing to do, I'm going to spin it up again and then turn it upside down. Yep. Sorry. Okay. Quite a brute to take upside down. Up to the marks. There we are. When you have seen that, you have seen something you have not seen before. Again, there was the same out of balance 2 kilograms. These gyros are getting larger, and of course, like electrical machines, as they get larger, they get better. Now, what was very interesting about that experiment, I'm about to show you. I'm going to modify this gyro by putting in a second pivot point. I screw that into there, and then the gyro into the end, and now the gyro has two alternative pivots. It can either pivot about there or about there. Okay? Which do you think it will elect to do? Bill? The gyro always knows the answer. Do that. It's never going to stay out there, is it? It'd be stupid to expect it to stay out there. Stupid, was it? Well, what about that one? Let's just have a look at what we've just done. The last thing I did was to take a gyro with a pivot there, another pivot there, and then the wheel. And we found that, of course, it elected for that to come down there like that, and the gyro to stick out there, because by doing so there was no change in the axis of spin of the gyro, no precession necessary. Why then did that work? Because there is a bench overhung. Here was an aluminium plate. The tower was completely outside the end of the table. A pivot there, the wheel there, and the second pivot there. This thing had the ability, if it wished, to do this and still remain with the gyro horizontal. Why did it not make use of the ability to go like that with the tower there and the gyro still horizontal? We shall see. This is the most remarkable experiment, I think, that I've ever done. I'll balance that, first of all, like a seesaw. So there is a balance point. When I take this out here, of course, then the balance point is upset. It should tip down. We know that given the opportunity, it's going to do this if it can, but now we've balanced it, and we've balanced it about its center of mass. So that if this gyro transfers its mass center to the pivot, it should stay balanced. The question is, will it? Let those who say I cannot make a body appear lighter than it is come and pull holes in that one. There's a lot of energy in this wheel. Now, we are now giving it hardly any fetters whatever. It's only tethered to the roof. It's got no gimbal rings. It can go any way it pleases. It must surely want to rotate with its center of mass over the point, under the point of support. Yep. Cranky man. The E.W.O isn't the only monster. Over the center of mass, over the center of support, there it goes. What will it do? "2001, A Space Odyssey." No less. Notice the angle it makes with the horizontal. It's tipped down a bit. In a moment you'll see it rise again. Now it's coming in on a shorter orbit, and the wheel axis is now beginning to tilt upwards. It is going to maintain its center of mass on a horizontal plane, even though as a conical pendulum it appears to have raised. Now it's actually going out again, and it will perform a number of these orbits from an outermost orbit to an innermost, and it reminds one of an electron, jumping from orbit to orbit, because they're said to spin also. If we have the patience, we'll see it come in again and rise up again, and the gyro wheel is slowing by its own pivot friction, and it is remarkable how low a speed you can get and still have the gyro staying horizontal when it gets close in. It is liable to get settled into a very definite orbit like this, which is the time when I move in and say, is he going back? Because he's only running very slowly, and I'm going to slow it still more because of our lack of time. Slow it right down till you can really see those spots, and then say, will you still maintain that that should be your axis of spin? And he says, yes, of course. Look at the rotational speed. It'll soon be down to the stage it's doing 1 revolution of precession per revolution of the rotor. And that is a most incredible machine. Something that you can try on a small scale with a toy gyro like this. Don't ever attempt it with this size, because it is very lethal indeed. On this stand there is a spring. On top of the spring you have a bearing which is free to rotate that way, or a linear bearing to make it go up and down, and we are going to couple this wheel into a pivot. Okay. Don't need to go very fast. No centrifugal force. I can make it rise, and as I do so, that spring says it weighs less. It looks a monstrous device with all that energy I told you about to have to catch with one hand. It's no problem at all. It has no angular momentum this way. I can lean down also casually and stop it. It is, as I said, as gentle as a lamb. I didn't give it any energy, so why should I expect to receive any from it? Okay, mate. Cool that one down. Are these discoveries new? Well, not entirely. I have had letters from all kinds of people who have done similar experiments before, and for one reason or another have given up for 1, lack of know-how and scientific background, 2, lack of money and workshop facilities, 3, lack of courage, 4, lack of anyone to listen, especially 4. Now today I've got all of you here ready to listen. What a pleasure it is to talk to young people who are ready to listen after you've talked to adults. Quite the most amazing letter I had was from a man who wrote quite unemotionally that he'd performed some of the experiments that I'd done some 10 years ago. And he knew that they worked, but he added, I've not told any of my colleagues or friends because even though I occupy quite a senior post in the scientific civil service, I still have a few years to go to retirement, and I still cherish hopes of further promotion. That is a hell of a thing to say in the scientific world, isn't it? This man dare not tell his colleagues. We talk about blackbirds pecking out the white feathers of their colleagues or killing them if they can't because they didn't conform. This man is afraid of being put away because he wouldn't conform. Now this is not the time or place to go into the mathematics of the gyros. This I can do also. It is not the place to attempt an explanation of the phenomenon, but I cannot send you away hungry, you who have come to listen and to learn. I'm going to go back to an electrical experiment. In this theatre someone said, Mr. Faraday, what use is all this? And he was my personal hero. He was the man who showed that Ohm's law was only all right for DC. I'm using this coil again. You put DC through it from a battery, and you get 4 amps and 8 volts. That coil has a property all its own, which we call resistance, Ohm's law. And with 8 volts and 4 amps, you get 2 ohms. Now we'll apply some alternating current to the same coil, and we'll get our same 4 amps. You got the wrong scale on, Benny. Can you put the scale right? We're not cheating. You can try this for yourself. This is obviously well known. The voltage is in fact 32. So now we have 4 amps and 32 volts, and we have apparently 8 ohms. We call them ohms, but they're not in Ohm's law. Ohm's law can't have 2 different values at the same time. The interesting thing is that over 140 years later, we don't say that Ohm's law was wrong. We simply say it is restricted to the use of DC. So, however distasteful it is, we now have to say that object has got something more than a mass. It's got a mass, and a mass only, so long as we want to push it about in straight lines, weigh it, accelerate it, so on. But if we ever choose to spin it, it has another property all of its own, which corresponds to the inductance of a coil. This is the updating of Newton's laws of motion. But I'm not saying that Newton's laws of motion are wrong. I'm merely pointing out they are restricted to motion in straight lines and to motion where there is no rate of change of acceleration, just as there was no rate of change of current for Ohm's law. So that is at least some food for you to think about, and some indication that I have very strong ideas as to how these things work. So I find no difficulty in saying this thing in a black box had a mass, an angular velocity, and no angular momentum, because we know that in a reactive circuit you have volts, amps, and no watts. What is so difficult at that? And if the abominable no men outside this theatre, this is one of the letters I received, a man called my critics abominable no men. They say no before they've even watched.